counters is another important sequential circuit, okay, and we use it a lot, okay, in sequential circuit design. And for this reason, I need to talk about it in great detail. We already have seen the counter before. Okay, when I talked about sequential circuit design, we have seen the state diagram. Okay, how we can actually go through a specific sequence of states. You can design it like this. Okay, you can design a counter using just the state diagram, and you can obtain the equations from the state table using the Carnot maps, and you can draw the circuit. That's something that you can do. But I'm going to show you a different way of designing counters. Okay, by understanding counters, it will make its design very easy and very simple. Type. So the output of the counter here is the count value. Okay, so that's the count value, which is shown at the output of the counter. And cycle by cycle, you see the clock here, it's connected. So cycle by cycle, we increment the count. So we start, for example, when you reset, you can start at 0, but next clock cycle it becomes 1, next cycle it becomes 2, and then you can actually go through n states. And if you have a modulo n counter, you can go from 0 to n minus 1, but once you reach n minus 1, then you go back to 0. Okay, so you go back to 0 after reaching n minus 1. For example, if you have modulo 8 binary counter, you are counting in binary, okay, from 0 to 7. So 7 will be 1, 1, 1. So basically, you are using 3 flip-flops inside this counter to count from 0 to 7. This is why it's called modulo 8. And once you reach actually 1, 1, 1, you go back to 0, 0, 0. Okay, so you continue like this. If you would like to design a modulo 10 BCD counter, you are counting from 0 to 9 and then back to 0. I will show you later, okay, next time, how we can design such a counter that will count from 0 to 9 and then back to 0. So we can skip, okay, from 10 to 15, and then we can jump from 9 back to 0. That's really not that difficult to be done. We can count up, we can count down. Yani, for example, if you have a modulo 8 counter, you can start at 7, then 6, then 5, and you can go down to 0. And once you reach 0, and then you can actually go back to state 7. Okay, so this is actually called countdown. So you are counting backwards. Okay, so you can design your counter to be counting forward or counting up, or you can make it to count backwards or counting down. So all of these are variations of counters. I'm going to show you some applications, okay, of counters. Well, there are many applications of counters that people actually use them in sequential circuits. For example, people use timers. Okay, timers are used a lot inside CPUs, inside digital circuits, and timers will keep track of time. So by counting the number of clock cycles, and for example, you can use here large N. Okay, so you can use large N and you can actually reach a large count. So by using a counter like this, you can count every cycle, and you know what is the clock cycle or the clock period. Okay, so therefore, based on that, you know what's the count value. So knowing what's the count value, you can keep track of time. Okay, so basically the count is changing cycle by cycle, and we know what is the duration of a single clock cycle, so we can keep track of time. Yani, for example, you might actually want to count 10,000 cycles, and then this will be used as a timer. Okay, so that's actually one application. Another application is to count the events. Yani, rather than counting cycle by cycle each clock cycle, you will count only when there is an event. And if there is no event, you don't change the count. So this is called event counting. You can also use the counter for frequency division. Okay, and I'm going to show you this in great detail next time. In other words, you can actually use the output of a counter as a clock. You can use it as a clock, but with a different frequency. So you can actually have a slower clock, okay, that has a longer clock cycle. That's called frequency division. You can use it, actually, you can implement frequency division using counters. So counters are really interesting, and we need to understand how we implement these counters. Okay. So let us see how we implement these counters. Okay, we have two basic approaches. We can use ripple counters. This is one implementation, or we can have synchronous counters. Today, I'm going to talk about ripple counters. Next time, I will go into the details of synchronous counters. So in the case of the ripple counter, the system clock is connected to the clock input of the first flip-flop. So this will be the least significant bit. And each flip-flop, its output is connected to the clock input of the next flip-flop. Okay. So I'm going to show you the circuit in a minute. But the advantage is that you have a simple circuit, really very simple circuit. You don't even need gates for that. You just need flip-flops and you wire them in a certain way. And this will be the if you would like, a low cost, okay, counter. Okay, it's the simplest type of counter. The main disadvantage is that the counter is not really truly synchronous. And we're going to see this also in great detail. Because we are not really connecting the clock to all the flip-flops. We are connecting it to only one flip-flop. And because of this, okay, we say that this is not synchronized with the clock, and you can actually get the outputs of these flip-flops delayed. So we have this ripple propagation delay. It's going to become clearer, inshallah, okay, in the next few slides. This is the ripple counter. On the other hand, we have the synchronous counter. I'm going to talk about them, inshallah, on Sunday. So they are called synchronous because we are connecting the clock to all the flip-flops. All of them are going to change at the same edge of the clock. So we are synchronizing all the flip-flops, and this is why it is called synchronous. Now, in order to increment the counter, we can use combinational logic, okay? And this is actually how it is used to implement synchronous counters. So we have to use some gates. Let me start first with the ripple counter. This is an example of a ripple counter. So this consists of 4 bits. You can see here we have a Q0, okay, Q1, Q2, Q3. So this is modulo 16. Modulo 16 because we can count from 0, 0, 0, 0 to 1, 1, 1, 1. So we count from 0 to 15 and then back to 0. Okay. Let me show you this in the next slide because this is clearer here. It's the same counter. Let us understand this counter. Okay, it's sometimes this is confusing to some students, but it's really, if you focus with me, I can actually show you how this ripple counter works. It's not really that difficult to understand this counter. Now notice that, okay, every flip-flop, notice that the clock here, okay, is connected to the clock input of the least significant bit only, to only one flip-flop. So this is my system clock, and therefore only one flip-flop is going to change every cycle. At the rising edge of the clock, then we change only Q0. How we are going to change Q0? Notice that this is a Q0 prime. And we are connecting Q0 prime back to D0. So if Q0 equal to 0, okay, then Q0 prime will be 1, right? So basically Q0 prime is nothing but the complement, okay, of Q0. The same thing, Q1 prime is the complement of a Q1, etc. Now, initially we can reset, okay, all of these flip-flops, and we can start at 0, 0, 0, 0. This is my initial. After we do a reset, okay, we start at 0, 0, 0, 0. Now, cycle by cycle, I'm going to increment my count. So how does this work? Notice that I'm connecting here Q0 prime back to D0. So this is nothing here but Q0 prime. So let me write here small Q0 prime. So if Q0 equal to 0, Q0 prime is equal to 1. So next cycle, we are going to change it to 1. So we call this, we are toggling or we are inverting Q0. But we are doing this kind of inversion at the rising edge of the clock. So this will happen at the rising edge because you see the clock is connected to the least significant bit. Now, this is now 1, right? So this is 0. Next cycle, we are going to change it from 1 to 0, then to 1, then to 0. So this is for the least significant bit, 0, 1, 0, 1, 0, 1. Cycle by cycle, we are inverting the output to Q0. And the trick is simple. Connect the Q0 prime back to D0. But here's the important thing. Okay, we are connecting also Q0 prime to the clock input, okay, of the next flip-flop. Okay, so you can see that Q0 prime is connected not only to D0, but also it is connected to the clock input. Now, this means that this flip-flop is going to change its state at the rising edge of the clock. But there is no clock. There is actually only Q0 prime. It's being connected to the clock input. Okay, so there is no common clock, okay, in this ripple counter. So we are taking Q0 prime and we are connecting it here. So this is nothing but Q0 prime. Now Q0 prime, notice that Q0 prime is going to change from 0 to 1 here. Now this is the rising edge of Q0 prime. When it changes from 0 to 1, that is considered to be the rising edge of Q0 prime. That's the positive edge of Q0 prime. Now, at the positive edge of Q0 prime, we're going to change Q1. So Q1 here becomes not Q1. So you see here, and this is a Q1 prime. This is actually connected back here too. So this is Q1 prime. So notice that how we are inverting Q1. But this will happen every 2 cycles, not every cycle. Okay, so maybe I need to clean up, okay, this to show you that this is really happening not every cycle, every 2 cycles. So here we have 0, 0, then we have 1, 1, then we have 0, 0, then this is 1, 1. So every 2 cycles, we are changing Q1. And this is because Q0 prime is jumping from 0 to 1 every 2 cycles here. So this is the rising edge of Q0 prime. Now, this is the rising edge of Q1 prime. So you can see that Q2 is changing at the rising edge of Q1 prime. So this is actually Q1 prime. And this is going to change every 4 cycles. So notice that's going to change every 4 cycles. And we toggle it every 4 cycles. So 4 cycles, it is 0. 4 cycles, it is 1. Then 4 cycles, it is 0, and so on. And finally here, you can see that this is actually Q2 prime. So Q3 is changing every 8 cycles. Okay? So if you do it like this, you have produced a count from 0 to 15. And once they reach 15, then basically you toggle all of them and they will go back to 0, 0, 0, 0. So that's my implementation, not my implementation. This is the implementation of the ripple counter. This is how it is implemented, okay? So it's a simple counter, as we have seen. Now, if I would like, notice that here that Q prime is just the complement of a Q. And if I would like to clean up this slide here, okay, let me clean it up. Erase all the ink. So notice that we start here 0, 0, 0, 0, and this becomes actually the complement, which is 1, 1, 1, 1. So as we are incrementing, okay, Q, we are decrementing Q prime. That's interesting. Okay, so basically we can have an up counter and we can have also a down counter. So as we are counting up the Q, we are decrementing Q prime. Okay. I can reverse them. I can decrement Q and I can increment Q prime if I want to. If I would like to count down, I can actually decrement Q and increment Q prime. And the way to do it is that we can just simply change the wiring. So rather than connecting, okay, Q prime, Q0 prime here to the clock, why not connect here Q0? So take this here from Q0 and connect it. So we have Q0 here, have a Q1 here, and have a Q2. If you do it like this, then basically the output of these flip-flops are going to be decremented every cycle. So the Q will be decremented and the Q prime will be incremented. So basically we can reverse, okay, the order of the counting in the ripple counter. Okay, do you understand this? It takes time, as I told you, it takes time to understand this because these flip-flops are not connected to the same clock. The clock is connected only to the least significant bit. And what is really confusing is that we're using the rising edge of a signal like Q0 prime and Q1 prime and Q2 prime to toggle to change, okay, the other flip-flops. Okay. If I would like to reverse this, I would like to make a Q to count down and Q prime to count up. We can actually simply connect Q0 here. We can take this Q0 and connect it to the clock input. I can take Q1 and connect it to the clock input. The same thing here for Q2, connected to the clock input. So what we have to do is that we have to change the wiring, and this way we can reverse the counting. We can make Q to count down and Q prime to count up. So it depends, of course, what you would like to do with this ripple counter. You can actually count up, you can count down. So both can be achieved, okay, depending, of course, on how you have done the wiring. So really, this is a very simple counter. If you just look at the values of Q and the Q prime, you will see how they are changing cycle by cycle. Now, even though it's very simple, okay, it has no gates, just flip-flops. There is actually a problem, okay, with the ripple counter, and this problem is shown in the timing of the ripple counter. So if you look at the timing diagram of the ripple counter, okay, notice that how the output is, the problem is with the delay and the flip-flops. Okay, so the outputs are not really truly synchronized by the same clock. So the ripple counter is not really a truly synchronous counter. This is its major drawback. Now, suppose that the delay in the flip-flop is delta. So I'm defining here delta. I'm defining here delta, which is the delay, okay, the flip-flop delay, okay? So these flip-flops have delays. So at the rising edge of the clock, notice that this is the rising edge of the clock. Now notice that the Q0 is changing, but it's not really changing immediately. It is really delayed by delta. So the delay of a Q0 is delta, okay? Now, because we are using Q0, in fact, Q0 prime in the previous slides, so Q0 and the Q0 prime are delayed. Okay, so because we are taking Q0 prime and we are connecting it here to the clock input of the next flip-flop, then we have to wait, okay, for the falling edge, okay, of Q0, because we are using Q0 prime. So we have to use here the falling edge of a Q0 so we have we are using it as the clock for a Q1. So notice that Q1 is delayed not by just 1 delta, by 2 delta, okay? So this is going to increase the delay, okay, for these flip-flops. And if you look, for example, at a Q2, we are using the falling edge of a Q1, which is already delayed by 2 delta, and then we add a 3rd delta, okay, for a Q2. So we can see that as we go from one flip-flop to another flip-flop, we are increasing the delay, okay? Because we are not really using the same clock to connect to all of these flip-flops. We are taking the output of one flip-flop and we are using it as a clock for the next flip-flop. So therefore, each output is delayed by a delta, and this is going to increase the delay from one flip-flop to another flip-flop, and this is the rippling effect, okay? So for this reason, okay, we say that the ripple counter is not really a truly synchronous counter because, okay, the outputs of these flip-flops do not really change at the same moment in time, or they are not really changed after the same delay. And for this reason, we have this kind of rippling effect. So as we add more flip-flops, you can see that the delay is going to increase more and more. And this is the major drawback of a ripple counter. Okay. Do you have any question about the ripple counter? Do you understand it now? Okay. I already have covered this last time, but if something is not really clear, you can raise questions now. Type. The second type of counter that I would like to talk about it today is the synchronous counter. So here we really would like to avoid rippling. Okay, and for this reason, what we are going to do is that we are going to connect all of these flip-flops to the same clock. So notice that here we have the clock connected to an n-bit register. So this n-bit register has all the flip-flops. So we place them inside the same register and we connect all the we connect the clock to all of these flip-flops. Now, in order to simply increment, okay, the count, we take the Q output, we use an n-bit incrementer, and therefore, if the output is a Q here, we get Q plus 1. So basically, at the next edge of the clock, at the rising edge, okay, if we're using a positive edge-triggered flip-flop, so at the rising edge, we're going to change Q to become Q plus 1, and we start counting up. Okay, so this is basically how we can implement synchronous counters this way. So all what we need is just an n-bit incrementer, which is just a combinational circuit that we have seen before, right? When we talked about adders, I talked also about incrementers. So if I would like to show the details are shown here in this slide. So for example, if n is equal to 4, I will have a 4-bit counter. So here n is equal to 4. Okay. And we have only 4 flip-flops. Notice that how the clock is connected to all the clock inputs of all of these flip-flops. So this indicates that this is truly synchronous counter. So this is why it's called synchronous counter, because it's synchronized. All the flip-flops are synchronized with the same clock. Now I need a 4-bit incrementer, as shown on top here, to increment the value of a Q. So Q here is the output of the flip-flops. It's the output of the counter. Okay, so the output of the counter is the output of these flip-flops. And we are implementing this 4-bit incrementer using half adders. Sorry, these actually are half adders. This is a half adder here, another half adder. Okay, so each half adder consists of an AND gate and XOR gate, and there is an enable input here, and there is a carry out. Now, these actually are important. I will explain them, why we need them. It's going to become more clear in the next few slides. So as long as enable equal to 0, if this enable equal to 0, then basically the output of this AND gate will be 0. So C1 will be equal to 0, C2 will be equal to 0, C3 will be equal to 0, C out will be equal to 0. Okay. And if the C inputs here, okay, if the carries are 0, if this enable equal to 0, then the output of this XOR gate is nothing but Q0. You get Q0 here. You get Q1 here. You are XORing 0 with Q1. You are XORing 0 with the Q2. So you get Q2, you get Q3. So basically, there is no change in the output of Q. So you are saying that next cycle Q becomes a Q, so you are not really changing Q. Okay, there is no change in the output of Q. So we can actually control whether to freeze the counter, okay, with this enable. This is the importance of this enable. So enable equal to 0, there is no change. If enable equal to 1, then we are going to increment. Okay, so let us now change this, remove this ink and change the enable equal to 1. Okay, enable equal to 0 is very simple. Do you have any question? Please interact with me if you have any questions. Okay, just you can stop me if something is not really clear. So really what we are doing is that we are using flip-flops and we are using an incrementer to increment the count. That's it. So let me erase this and use enable equal to 1. So I'm going to write 1 here below enable. I'm going to put 1. See, this is 1, right? Now, if this enable equal to 1, look at the value of a Q0. Now, if you have a Q0 and you XOR it, so notice that the Q0 is going to appear here. It's going to appear as an input here to this XOR gate. So when you XOR it with 1, you get the Q0 prime. Now, when do we get C1 is equal to 1? If a Q0 equal to 1 and enable equal to 1, then you get C1 is equal to 1. And when you XOR C1 with the Q1, you get Q1 prime, and so on. So if you look at this, the way that this 4-bit synchronous counter works is that if enable is equal to 1, then the D0 becomes equal to Q0 prime. So cycle by cycle, we are going to invert the output Q0. So if Q0 was initially 0, then it becomes 1. And if it became 1, the next cycle it becomes 0. Then 1. So 0, 1, 0, 1, 0, 1. That's basically is Q0. Yeah. So this is actually showing here in this cycle. Okay, in this slide, sorry. You can see that cycle by cycle, now we are toggling the value of Q0. It was initially 0, then next cycle it is 1, then 0, then 1, then 0, then 1, etc. Okay. Now, when Q0 becomes 1, okay, if this Q0 is equal to 1, let me put 1 here on top of it. Let me just erase this. So if this Q0 is equal to 1, then this is 1 here, and enable equal to 1. This will give me C1 is equal to 1. And we get a carry, because this is a half adder. This 4-bit incrementer is made out of half adders. So we get this C1 is equal to 1, and therefore this C1 with this XOR gate, we have XOR gate here. So when we XOR with 1, you get the Q0, we get Q1 prime as the input to D1. Okay, so if this C1 equal to 0, you get Q1. If this C1 is equal to 1, you get Q1 prime. You are actually inverting. You are using this XOR gate to invert. So you are complementing Q1. You get Q1 prime. So this is shown here. So when Q0 is equal to 1, okay, then we are toggling the value of Q1. This is explained here. So when Q0 is equal to 1, you toggle. Toggle means that we complement the value of Q1. Now notice that, again, back to this slide. If you have Q0 is equal to 1 and Q1 is equal to 1, if both of them are 1 and 1, okay, then basically you get another 1 here, and you get C2 is equal to 1. So once you get C2 equal to 1, then the input D2 becomes a Q2 prime. So this XOR gate is used to invert Q2. It becomes a Q2 prime. So therefore, we are going to complement Q2. Next cycle, we are going to complement Q2, as shown here. So when you have Q0 is equal to 1 and Q1 is equal to 1, the next cycle, we are going to toggle the value of a Q2. Okay, so we complement here Q2. And when you have Q0, Q1, Q2 are all equal to 1, then next cycle, we are going to toggle the value of a Q3. Okay, so this is how it works. And because of this, we are counting from 0 to 15. And when all of them become 1, let us take a look when all of them become 1 in the previous slide. So when all of them are actually 1, so we get 1, 1, 1, 1, then we are getting here, okay, so we are getting C3 is equal to 1. And this will give me Q3 prime. And of course, C out will be equal to 1. This is when you get C out. You get C out equal to 1 when you have all the outputs have reached 1, 1, 1, 1. So when the count becomes 15 and it is enabled, and all of them will become, so here we have 0, 0, 0, 0. This is basically is Q prime. It's the complement of a Q. And next cycle, we jump here from 1, 1, 1, 1 back to 0, 0, 0, 0. So we toggle all of them. Okay, next cycle. Okay, so that's basically how the counter works. Okay, so you can think about the counter as consisting of flip-flops and an incrementer for just incrementing the count, or you can think about it as toggling, okay, the output. So it was the output Q0 was initially 0, then it became 1, then 0, then 1. So we toggle Q0 every cycle, okay, if it is enabled. We toggle Q1 not every cycle, as we have seen here in this slide. We toggle it every 2 cycles. So when Q0 becomes 1, then we toggle Q1. We toggle Q2 every 4 cycles. So 4 cycles, it is 0. 4 cycles, it is 1. So you have to wait until Q0 and Q1 become both 1 and 1 so that you can toggle Q2 In the case of Q3, we toggle Q3 every 8 cycles. So we wait until Q2, Q1, and Q0 are all zeros. Now, you can do it with D flip-flops, as shown here. You can see the type of the flip-flop is D, and we are using these XOR gates, okay, to invert, okay, the output Q, because when you XOR with 1, you are toggling, you are inverting. Or you can bring this XOR gate inside the flip-flop. It becomes a T flip-flop. So the T flip-flop is the toggle flip-flop. That's another way of implementing, okay, the counter, is that we can use the T-type flip-flop. So T here means toggle. If the input is 0, you don't toggle. If the input is equal to 1, you are actually toggling. Okay, so you can see that we are simplifying the logic into just AND gates so that we can propagate the carries, okay, from one flip-flop to the next. Okay, so if enable is equal to 1, so if this enable equal to 0, then there is no change. Okay, so this will be 0, and therefore there is no toggling. If this is 0, this will be 0, this will be 0, this will be 0, this will be 0, right? Because we are actually ending with 0, regardless of Q. So if the enable equal to 0, we are freezing the count. There is no change in the output Q. So we're not really counting. On the other hand, let me erase this ink now and replace enable with 1. See? Yeah. Here we go. I'm losing track of my mouse for some reason. I don't really find my cursor. But anyways, let me just erase this here. Okay. So let me replace this here with 1. So let me remove these zeros one by one and place a 1. So if you have a 1 here, it means that I would like to increment my count. So this actually T input is 1. It means that we are going to toggle, okay, Q0. So if T0 was, if Q0 was 0, then it becomes 1, then it becomes 0. Okay, so 0, 1, 0, 1, 0, 1, that will be for the output Q0. Now when Q0 becomes 1, so you have 1 here, you have also 1, then C1 becomes 1. So this makes T1 becomes 1, then we toggle Q1, okay? And so on. If Q0 equal to 1 and the Q1 is equal to 1, so we have 1 and 1 here, then we get actually here C2 is equal to 1. So when T2 is equal to 1, then we are going to toggle Q2. And when you have 3 1s here, you get also a 1, and this will toggle Q3, as we have shown in the slide here, okay? So that's basically exactly how it works. But you can think about it that you are toggling or you are complementing, okay, the output to Q. So what we have seen is that we have seen a counter, okay, which actually counts up. There is something which is about counting down. Let me just go backwards. You see here, I have a question, is that how do we count down? Let me clean up this slide here. So how do I count down? The answer is shown here in this slide, is that we have a 4-bit incrementer. But rather than incrementing the Q, you see that how Q is connected to the incrementer? It's actually connected. You can see how it's connected to all of these. These actually are really half adders. This is a half adder here. This is another half adder, etc. Okay, so rather than connecting the Q to the half adder, I can connect here Q0 prime. This is Q1 prime, Q2 prime. So we can take these and we can feed them back. I can take this and feed it back. I can take this and feed it back. So rather than incrementing, okay, Q, I can increment Q prime. And if we increment Q prime, you are actually simply decrementing Q. Okay. So that's basically how we can decrement the counter by incrementing Q prime. So, so really they work, okay? So if you increment one, you are decrementing the other. If you increment Q, you are decrementing Q prime. If you increment Q prime, then you will be decrementing Q. It's a simple trick that we can do. Just change the wiring, increment Q prime, and this will decrement Q. Okay, so now, how about if I would like to design a counter that can count up and down? I can control it. Sometimes I would like to count up. Sometimes I would like to count down. Okay, well, we can have two inputs here, up and down. We can use the same T flip-flops that we have seen in the previous slide. So these are T flip-flops. You can see the T input. Okay, so these actually are T inputs. Now we can use these AND gates, which are shown here. So let me use here the AND gates to produce the carries as we did before. So here up is actually my enable. In the previous slide it was called enable. So if this is equal to 1, then basically it's going to count up. Notice that if this is equal to 1, we have an inverter here. This will be 0, this will be 0, all of these will be zeros. So forget about the gates that appear to the left. Focus on these gates, these AND gates, and notice that how we are connecting Q0, Q1, Q2, okay, to all of these gates. We can also have another AND gate for C out if I would like to add C out. So I'm connecting Q0, Q1, and Q2 to these AND gates, and this way we toggle, okay, when Q0 equal to 1, then we can toggle Q1. If Q0 and Q1 are both equal to 1 and 1, I can toggle Q2, etc. Now, in the case of counting down, I have to make up equal to 0. So this must be equal to 0. So this will be 1. And this will be 1. Okay, then this will be 1. Now, if this is 0, let me actually just put zeros here. So if this is actually 0, okay, so here we have 0, right? So all of these will be zeros. Now here, this will give me my carries. Okay, carry 1, carry 2. So this will be C1 for the next flip-flop. This will be C2. This will be C3. Okay, it will be actually the carry, but I'm connecting here, okay, Q0 prime. You can see these actually are Q0 prime. How they are connected to this set of AND gates, to these AND gates, which are shown to the left. And these are going to be used to toggle, okay, the flip-flops. Now notice that we have two sets of AND gates. One is used to count for counting up. The other one is used for counting down. I need to order them. So if anyone says toggle, then we toggle, okay? So either we choose the ones which are on the left or we choose the ones on the right. So this is why we need to have OR gates, which are shown here, okay, to connect them, because I cannot really wire their outputs. I cannot connect two gates to the same T input. So this is why we have to OR them, and then we can connect to the T input. So we can design, okay, such an up-down counter, okay, to count up and to count down. Okay, so this is how it is implemented. And I'm implementing it using T flip-flops. All right, questions? Anyone has a question? For those who are actually present, I know that only few are present. Yes, Hamma?
Can we use just multiplexer?
We can, but OR gate is simpler than a multiplexer. Now notice that we cannot actually have both of them are enabled at the same time, because in the case either you actually have up is equal to 1 or down equal to 1. So one of them, so you have at least one of them will be 0 and the other one is a 1. You can actually have 0, 0. It's also possible. And if you have actually 0, 0, it means that we are not really counting up or down. So this is going to freeze the count. You can actually use a multiplexer, but then in this case, you have to actually select based on up or down. So it will be a lot easier just to use an OR gate. Okay. Remember, in the case of multiplexer, you can also implement multiplexers using AND gates and OR gates. It's the same thing here. Okay. There is no need. Actually, you can actually replace this actually here, right? With a multiplexer. You can replace this with a multiplexer. You can replace this with a multiplexer. If this is what you mean, right?
Yes.
That's also is possible. It is also possible. It will change the implementation slightly, but yes, it is actually possible. And you can select whether actually to connect Q1 or QZ, but you have to make sure that you are ending it because there's actually carries which are propagated. So it's a lot simpler to implement it like this. Okay. Right. So remember that in the case of counting down, okay, we are using Q0 prime. So when Q0 is equal to 0, Q0 prime will be equal to 1. Okay, so this must be equal to 0. Then this will be equal to 1. And because actually we are counting down, so when we get this is equal to 1 here, and we get a 1, then we get C1 is equal to 1 here. And we get a 1 here, then we are going to toggle Q1. Okay. And when you have this is equal to 0 and this is equal to 0, then you have actually 1 and 1 here. Then you get C2 is equal to 1. You get the output here equal to 1. And you can use this to toggle Q2, etc. Okay. So this is basically how you can count down. And it's clearly shown here, okay, that 0, 0. Okay, how you are going to toggle this one. Okay, 0, 0, 0. You can actually use it to toggle Q3. This is going to be used to toggle Q1. So basically, you can actually count backwards, okay, this way. So this is basically how you can design a counter that can actually count in both directions. It's messy now, okay? So let me clean it up again. So the same counter can be used to count both up and down, and we can control it with 2 inputs here, up and down, okay? So in the case of up equal to 1, then we are counting up from 0 to 15. If up equal to 0 and down is equal to 1, then we are going to count backwards, okay, from 15 down to 0 and then back to 15, okay. And if you have them 0, 0, then basically we're not really counting up, we're not really counting down. This will freeze the count. And of course, 1, 1 means up, because if this is 1 and this is 1, okay, notice that there is an inverter here. This will make it 0. So this will force the output of this AND gate to be 0. So this will be zeros here. And therefore, we are going to use up. So this one is going to appear here. Okay. And therefore, so if up is equal to 1, we don't care about down. Whether down is equal to 0 or 1, it does not really matter. Okay. We are going to count up. If up equal to 0, then we look at down. If down is equal to 1, then we are going to count down. If both are 0, 0, then we don't really change the output Q. We just keep it as it is. Now, the nice thing about the synchronous counter is that all the flip-flops are driven by the same clock. You can see that in the previous slides. You can see the clock here is connected to the C input of all of these flip-flops. So this is truly synchronized. Notice here how the clock is connected to all of these flip-flops. Okay. Again, let me go back. You can see the clock connected to all of these flip-flops. So what this means is that at the same rising of at the same edge of the clock, then all of these flip-flops are synchronized with the same edge of the clock. So the delay, even though these flip-flops might have a delay, but the delay is the same, is identical, okay, in all of these flip-flops, and it's equal to delta. And for example, this is delayed by delta. This is also delayed by delta. Okay, all of these here are Q0, Q1, and the Q2. All of these are delayed by delta. All of these here are delayed by delta. It's the same delay And that's actually is the beauty of the synchronous counter. It's all the flip-flops are synchronized by the same clock. So we don't really have this rippling effect that we have seen in the rippling counter. Okay. So that's actually the clean, okay, truly synchronous counter. Okay, so let us move on. Now, one interesting application of counters is a frequency division. You can use a counter as a frequency divider, which means that if you look at the outputs of the counter, you can take actually each flip-flop and you can look at its output. You can look here at the output Q0, you can look at the output Q1, Q2, Q3, etc. Okay. Now, let us take a look here at the output Q0. So now, the output Q0, you can see that here Q0 is going to change every other cycle. So you can see that here, if this is actually has a clock frequency, which is F. Now, notice that if you look at the Q0, you can see that it has the same waveform of a clock, even though it's delayed by delta. But you can see that the clock period, okay, is twice, okay, the clock period of the clock. So if this is, for example, T between here and here, okay, so sorry, between two, let us say between two rising edges. Let me just erase this. So let us take a look here between these two edges. These are two rising edges. If this is T, so this is actually T here is my clock cycle, then this will be between these two edges here, will be 2 times T, right? It's double the clock cycle. Because it's double the clock cycle, notice that between, for the Q1, between these two rising edges, it's 4 times T. It's 4T. And for Q2, it's 8 times T. Okay, so basically, if you look at these outputs, Q0, Q1, and the Q2, Q3, you can see Q3 will be 16 times T. So basically, you are doubling. So the outputs are also, okay, like a clock. Okay, there are periodic signals that have exactly the same shape like a clock, but the cycle is increasing. It's actually doubling. So it was the clock cycle, it was T. In the original clock cycle, it became actually in Q0, it became 2T, then 4T in Q1, then 8T in Q2, etc. If you look at the frequency, if the frequency of the clock is F, now the frequency is 1 over the clock cycle. Okay, so this will be F divided by 2. Because we are doubling the clock cycle, then we are reducing the clock frequency. So we are dividing it by 2. Now this clock frequency will be F divided by 4. This will be F divided by 8. And this will be F divided by 16 for Q3. So notice that the clock frequency is reducing, okay, because we have less number of cycles per second. So the clock cycle is expanding, but the clock frequency is reducing. Less number of cycles per second. That's the meaning of the clock frequency. So you can use a counter as a frequency divider. You can use it to divide the frequency. And if you would like to slow down a clock, use a counter to slow it down. You can actually obtain the output of the counter, okay, as a slowed down clock. You can reduce it by half, by a quarter, okay? So you can divide it by 2, by 4, by 8, by 16, etc. So that's really the idea of frequency division. Any question about this topic before I move on to the next one? Type. It seems that everything is easy. Okay. So let us talk about BCD counter. Okay, so a BCD counter, okay, it's called BCD because it's a modulo 10 counter. It counts from 0 to 9 and then back to 0. So we are going to skip 10 to 15. If you use a 4-bit binary counter, it's going to count from 0 to 15 and then back to 0. But what we can do is that we can convert a 4-bit binary counter to become a BCD counter. And this is the trick. Okay. The trick is actually to use a reset. Now we know that all the flip-flops inside the counter are connected to a reset. Now we have two different types of resets. We have the reset here is synchronous, or it can be asynchronous. Now the idea is that if you are counting, okay, notice that the enable here is connecting to 1. You can enable it or you can disable it. So as long as enable is equal to 1, we are going to count up. So when you do a reset, you start at 0, then you count 1, 2, until you reach 9. Now, when you reach 9, you don't really want to go to 10. You would like to go back to 0. So what you do is that you try to detect here the output 9. So this will be 1, 0, 0, 1. That actually is 9. So you take this 1 and 1, okay, these two wires here, okay? So the first time you encounter 9, and you connect them to the reset input. So you take the output. So when this becomes 1, so you get here, you focus on the 1s. So we get this wire equal to 1 and this one equal to 1. Then this is the time to reset. So when you reset, if this reset is synchronized with the clock, at the rising edge of the clock, we are going to go from 1001 back to 0000. So this will reset it from 9 back to 0. And we start counting again. And every time we reach 9, the next cycle we reset back to 0. Now notice that I said that here the reset is synchronous. It is synchronized with the clock because we don't reset immediately. We reset, okay, at the rising edge of the clock. So that's actually, if you have a 4-bit counter with the synchronous reset, how you can actually convert it to become a BCD counter. Now, if your reset is not synchronized with the clock, you have asynchronous reset, then what you have to do is that you don't really count to 9. Because if you count to 9, the 9 becomes 0. You have to wait until it reaches 10. So you have to actually look at 10 here as 1010. That's actually 10 in binary. So you look at these two wires, okay, when they become both 1 and 1, okay, then this is basically when you would like to reset. But this reset is immediate. So at the beginning of the cycle, once at the rising edge of the cycle, okay, so it is changing from 9 to 10, okay, at the rising edge of the clock. So once it sees 10, then the 10 is going to reset immediately without waiting for the next rising edge of the clock. So the 10 is going to become 0000. So therefore, the 10 is going to appear momentarily at the beginning of the cycle, and then you are going to reset, okay, to become 0000, and then start all over again. So it's going to count from 1 to 9, and then 10 becomes 0, okay, during the same clock cycle, because the reset is asynchronous. It's not related to the clock. It will reset immediately. Okay, students. So you can see that we have changed the counter. Okay, we have converted the 4-bit counter. It was a binary counter that would count from 0 to 15. And now it's counting from 0 to 9 and then back to 0. Okay, so that's a BCD counter. That's good, okay, because sometimes I would like really to count in BCD. I don't really want to count in binary. Fine. So now let us actually see how we can build a large counter. Okay, so what we can do is that if I only have 4-bit counters, which are capable of counting from 0 to 15, what about, okay, counting, okay, from, let us say I would like to build a 12-bit counter, capable of counting from 0 to 4095. Now, 4095 is 2 to the power 12 minus 1. That would be the maximum 12-bit value which we can reach using a 12-bit counter. In order to implement, to design such counter, I can take advantage here of cout and enable. You see, I talked about cout before and enable, but now we are going to start using them, really. So what we can do is that we can take 3 4-bit counters and I can actually cascade them. Connect here. So we have the least significant 3 bits here, Q3 down to 0. We have the middle 4 bits and we have the upper 4 bits. So in total, we have 12 bits. Okay. But each 4-bit counter is only producing 4 bits. But I really would like to count from 0 to 4095. Of course, I'm going to count them in binary because the output is shown in binary. Right, so what we need to do is that we need to connect this C out to the enable of the next 4-bit counter. And this C out is connected to the enable of the next 4-bit counter and so on. If you do it like this, then this C out here, you produce equal to 1, not every cycle. So once you reach here 15, 1, 1, 1, 1, and this enable is equal to 1. Okay, suppose that the first enable is always 1, it's always enabled. You can, of course, disable if you want to. Okay, but once we have enable equal to 1 and the output Q is 1, 1, 1, 1, this is when you get C out equal to 1. So you enable the next 4-bit counter, and this is going to change from 0, 0, 0, 0 to 0, 0, 0, 1. Okay, so notice that how we have changed the output of the next 4-bit counter from 0, 0, 0, 0 to 0, 0, 0, 1. Now, this is done once every time we have finished 16 counts. Now, this is going to change back from 1, 1, 1, 1 to 0, 0, 0, 0. So once this goes back to 0, 0, 0, 0, this will go back to 0, right? And repeat. So as long as this is counting from 0 to 15, this is still 0 until it reaches 15. So once it reaches 15, it goes back. It wants to go back to 0. Then we increment the next 4-bit counter, and so on. So you see that this middle 4-bit counter is incremented once, okay, every 16 cycles, okay, after finishing 16 counts in the lower 4-bit counter. And what you have to do is that you have to wait for both of them to become 1, 1, 1, 1, and this is 1, 1, 1, 1, to get C out equal to 1 here, and this is equal to 1, to enable, okay, the upper 4-bit counter. So this is going to change from 0, 0, 0, 0 to 0, 0, 0, 1. So the upper 4-bit counter is going to change once every 256 counts. 16 times 16 equal to 256. So until you get the C out, okay, on the middle 4-bit counter equal to 1. So the middle has reached 1, 1, 1, 1, and wants to go back to 0, 0, 0, 0. This is when you get the C out equal to 1, and you enable the upper 4-bit counter. Okay, so this way, by this simple cascading, okay, of these 4-bit counters, I can build a large 12-bit counter this way. Notice that the clock, the same clock, is connected to the clock inputs of all of these 4-bit counters and all their flip-flops. And the reset is the same thing. We can reset all of them at the same time. Now, let me show you a different type of a 4-bit counter. Okay, so this counter has a load input, and it has here input data. Okay, we did not really have this in the previous counters that we have seen, and it has this load. Okay, this load input is to control whether to load the data inside the 4-bit counter. So the 4-bit counter has flip-flops exactly the same way that we have flip-flops inside a register. So we can load the data into these flip-flops. So if this is a 4-bit counter, 4-bit here means that we have 4 flip-flops. So if load is equal to 1, we can load the data inside these 4 flip-flops. So think about these flip-flops like a small register consisting of 4 bits, and we are loading the data into this 4-bit register, which is inside the counter. Now, if load equal to 0, we can use enable here to enable the count. If enable equal to 0 and load equal to 0, then basically we are not really counting, we are freezing the count. Now, this type of counter that has a load input will be very useful to implement different counting sequences. This is the importance of having a load input and a data input. Right, let us see how we can implement this 4-bit counter, and then I'm going to show you how we can use it in certain applications, in certain counters. The implementation is easy. Already we have seen the implementation of counters before, but now we have added this data input. So here my data input consists of 4 bits, D3, D2, D1, and D0. These are connected to a multiplexer. Notice that this is input 1 of a multiplexer. So if load is equal to 1, we select the data input is going to appear at the D input of all of these flip-flops. So these are D-type flip-flops. So if load is equal to 1, then we are going to load the data inside these flip-flops. That's the meaning here. The action will be to load data regardless of enable. Notice that I don't really care about this enable input here. It can be anything 0 or 1. It does not really matter. We are simply loading the data inside the flip-flops. Okay, so this is the meaning of load equal to 1. On the other hand, if load equal to 0, if this is not equal to 1, if this is equal to 0, there are 2 cases. Either enable equal to 0 or enable equal to 1. So if this enable is equal to 0, then okay, we are not counting. Okay, so therefore there is no change in the output of the counter. If enable is equal to 1, then we are going to increment this counter. So what we have here on top, this is a 4-bit incrementer. So the logic we have already seen before, that is going to increment, okay, the count, and therefore we are going to cycle by cycle at the rising edge of the clock. Notice the clock here is connected to the clock input of all these flip-flops. So therefore, at the rising edge of the clock, we are going to increment the counter. Okay. So this is the implementation of the counter with parallel load. Okay. So okay, it's a different type of a counter. It's the same counter that we have seen before, but I did a simple modification by adding a load input, and we can load the data inside the flip-flop so that we can initialize the counter with any value. We don't really have to start at 0. We can start at any input according to the data, and then we can start counting up. Okay, students, you have any question about this? Now, let me show you how you can use it, okay, to build a counter. For example, I can build a counter that will count from 3 to 12. I don't really have to start at 0. So we can take this 4-bit counter that has a load input, okay, and this is my external data input, and I can use it to count from 3 to 12. So how do I convert it to count from 3 to 12? It's not really that hard at all. Any idea about this? How to convert this 4-bit counter to count from 3 to 12? Anyone would like to answer this question? It's okay, any answer will be okay. Now notice that I would like to start at 3. So I can simply load, okay, the input 3. I can actually have it as my data input. So initially, we can start by loading 3, and then once we detect 12, we can load again 3. It's simple. It's not really that 12. So we detect the binary count, which is 12, and then we load 3. So if we would like to detect a 12, 12 is in binary is 1100. So this is 1, and this is 1, and this is 0, and this is 0. Now, what's important for us is to detect the 1s, not the 0s. So as we are incrementing the count, the first time we reach here Q3 and the Q2 are equal to 1 and 1, we get here output equal. So this AND gate, its output will be equal to 1, and this load will be equal to 1. And we load here 3. Okay, so 30011 in binary, we loaded into the counter at the rising edge of the clock. So the load here is synchronized, okay, with the rising edge of the clock. We can also have a preset input. This is important if I would like to initialize the counter. So I don't really want to start at 0. I would like to start at 3. So the first time I'm using this counter, I would like to say preset, and this will load 3 into the counter, and we can start at 3, and then we can start enabling this count so that we can actually count up. And once we have reached 12, then we can load 3 again into this 4-bit counter. So 12, then we go back to 3, and then we continue counting up 3, 4, etc. until we reach 12, and then back to 3. So the 12 will be detected based on a Q3 and a Q2 because 12 is 1100. So I'm taking these two outputs, Q3, Q2, using an AND gate. And once we have detected that we have the 1 and the 1 here for Q3 and the Q2, it means that we have to load 3 again. Okay, students, do you have any question about this? So that's a counter that can count from 3 to 12. You can change the sequence if you want to. You don't really have to start at 3. You can actually start at any number. You can start at 4, at 5, and you don't really have to stop at 12. You can actually stop also at any other number. For example, you might decide to stop at 10. Okay. So you see that it's not really that hard to build these kind of counters that can count for any sequence. Right. Let us move on. Okay, so here I would like to design a counter that will count from 9 to 99. Now the problem here is that 99, okay, cannot be implemented using a 4-bit binary counter because the maximum value, if you use only 4 bits, okay, 4 bits in a binary counter, you can go from 0 to 15. You cannot really go above 15 if you are using only 4 bits. So what you need is that you need more bits, okay, to implement the 99. Okay, so how many bits do I need for 99? Students?
7.
Exactly 7, yes, 7. But I might not really have a 7-bit counter, okay? So I need a 7-bit binary counter, okay? 7-bit can actually count to 127. I can start from 0 to 127. So 7-bit binary counter will do, okay? It will be, this is the type of counter that I need. But the problem is that I might only have 4-bit binary counters. And for example, I might not really have in my library, okay, a 7-bit binary counter. I only have 4-bit. So what we can do is that we can take 2 of them to build an 8-bit counter. So this is my first 4-bit counter. And this is my second 4-bit counter. Notice that the output C out here is connected to the enable. And this way we can implement an 8-bit counter. So if I only have 4-bit counters, then I can use 2 of them and I can cascade them to build a larger counter that consists of 8 bits. So here we have the least significant 4 bits, and here we have the next 4 bits. And the most important thing is that we took the C out and we made it connected to the enable of the next 4-bit counter. Now the clock here is connected to the clock inputs of both 4-bit counters, so both of them are using the same rising edge of the clock. This is when we change the state. This is very important. Now I would like to detect 99. And I would like to load 9. 9 is easy. Okay, it will be 1001. 99 is this number in binary. So this number in binary is 0, 1, 1. Here I have 0. And this will be 0, 0. And this will be 1, 1. So what is important to me is that to focus on the ones, Q6 here, Q5, here I have Q1, here I have a Q0. So these 4 outputs must be all ones at the same time. This will indicate that we have reached 99. So I focus on the ones. I need a 4-input AND gate. So the first time we encounter, so when we encounter 99, okay, then the output of this AND gate will be 1. And because here we have an OR, okay, so 1 or anything will give me 1. So therefore, we are going to load 9. So this is 9 here, and this is 0. Okay, so once we have reached 99, next cycle at the rising edge of the clock, we are going to load 9. So we go from, initially we can use a preset. This preset is going to initialize the counter to 9. So we load initially 9, and then we start enabling the counter. So the counter is going to count up until it reaches 99. Once it reaches 99, then we are going to reload 9 again and start all over again from 9. So next cycle, so we go from 99 back to 9, and then we go 9, 10, 11, etc. until we reach 99, and then we go back to 9 again. So you can see that we have here implemented, okay, a counter that will count from 9 to 99. I used 2 smaller 4-bit counters, and they are cascaded to build a larger counter because I might not really have a 7-bit counter. So for this reason, I use 2 4-bit counters. This will give me 8 bits, which is sufficient, okay, to count to 99. And then once we have detected 99, we went back to 9. Any questions about this? You see that actually these are like counters that is custom made according to your needs in your design. So you can really build all of these types of counters according to your need.